Good evening once again. This is Dr. Belga Burke, faculty member at Department of CSE, AI and ML and Cybersecurity, Jain deemed to be University. Welcome to another session of our Industry Connect program. Today's guest speaker, Mr. Daawood Sheikh M, is an expert in Python, R, and data analysis. He has more than 7 years of experience in cloud computing, business intelligence, and data analysis. He has a post-graduation in business analytics from Great Lakes, Chennai. Mr. Dawood has various certifications like AWS Developer Associate, Snowflake Professional, and Oracle Cloud certification to his credit. Currently, Mr. Daawood Sheikh is a senior data engineer at Accenture. Today, he would interact with you on the topic Unsupervised Machine Learning Algorithm, Spectral Clustering. Welcome, Mr. Daawood Sheikh. Please take over the session.
Sure. Thanks, Dr. Bilga. Thank
Yeah.
you.
Sir, we would like to request you to turn your video on if
Sure.
it's
Yeah.
possible.
Yeah. Sure. I'll do it. Yeah.
Yeah.
Okay. Perfect. Let me go ahead and share my screen. Okay. Are you guys able to see my screen?
Yes.
Thank you. Great. Good evening, students. So today we'll be discussing about unsupervised learning. Okay. And before we move on to the topic, okay. So what is unsupervised learning? I hope you guys will be aware of supervised learning, right? So you should not be saying what is supervised learning is. Supervised learning is nothing but if you have a labeled data set. So what is labeled data set? It's nothing but in your supervised learning, you will be having a data, a small amount of data called as trained data, where you will be having your outcomes node. So that is nothing but your dependent variable. Okay. If you know your dependent variable and if you train your model to learn from that dependent, that small trained data set, and if you try to predict the outcome of the unknown data set, right? So that is called a supervised learning. But whereas unsupervised learning is nothing but it does not have any labels. Okay, so you just have a blank data like here. So you'll be just having a blank data where you'll be passing it to the directly to the algorithm, and the algorithm will naturally predict the clusters or it could be anything. Okay, it could be either be clusters or association related to the data set. Okay, so that is called as unsupervised learning. Okay, you no need to supervise the model set. Okay, and what the algorithm does is it learns the characteristics of the data set and it tries to detect the patterns available in the data set. Okay, so this is called as an unsupervised learning. Okay, so what are the different examples of unsupervised learning? So first one is clustering. Okay, what is clustering? Clustering is this will be the topic which will be going in deep, okay, in this session, but for now I'll just give a quick introduction about what is clustering. So what is clustering is it divides the data set into different groups depending upon the pattern present in the data set. Okay. The next one is association. Association is nothing but the famous example is market basket analysis. Okay, where you in any e-commerce site or even in a supermarket, right, where you will be seeing the association between two different products. Say for example, it could either be a bread and jam. You'll be always seeing an association. The based on the depending upon the customers likes of getting that item. So you'll be seeing always the bread and jam together. Similarly, milk and eggs, those stuffs it could have been placed together. So that is why it's depending upon the buying pattern of the individuals, they'll be creating an association in the markets. Okay, that is called as market basket analysis. Perfect. Next, let's move on to anomaly detection. Okay, anomaly detection is nothing but based on the historical data set. Okay, you will be passing the historical data set to the ML model and you'll be detecting the anomalies present in the data set. Okay, either it could be the time in which the fraudulent transaction is happening, or it could either be the place from which the fraudulent transaction is happening. So those steps you will be able to detect it using the unsupervised learning. Okay, then what you'll be doing is you'll be passing the live data. So the live data will be passed on to the anomalies, sorry, detection anomalies, where you will be detecting the which type of problem you're going to face. Okay, so the next one is the dimensionality reduction. So dimensionality reduction is most probably this will come in the EDS stuff. So what you'll be doing is If you have multiple features, say for example, you have close to some 100 x variables, okay, if you have close to some 100 variables, x variables, and you don't know the importance of those x variables, so what you can do is you can just pass it to the unsupervised learning algorithm. So what it will do is it will highlight the important ones and it will create a new feature for you. So those features you can pass it to the model to predict the outcome of it. Okay, so this is called as dimensionality reduction. Perfect. So now let's deep dive into clustering algorithm. Okay, so clustering algorithm is nothing but it is the most common or important unsupervised learning technique, guys. Okay, so what it does is it learns the data set. You pass the raw data. It does not have any labels or training data set. Nothing is there. You just pass it to the algorithm. It learns from the data set what are the different patterns available in it, and it just clusters the data into multiple groups based on the different categories available. Okay, so there are two types of clustering. Okay, one is soft clustering and one is hard clustering. Okay, soft is nothing but first let's cover about hard clustering. Okay, hard is nothing but it's binary based. It's always 0 or 1. You can either group the class in either two zeros, or say for example if you have two classes, okay, one is class A and class B, you can either present that particular data point to a class A or class B. But whereas soft is probability based. For example, if you have three classes, okay, class A, class B, and class C, if you assign a probability of 40% to class A, 35% to class B, and the remaining 25% to class C, okay, what you'll be doing is, in case if you predict it wrong, say for example, class A is wrong, right? What you can do is you can just change it to the next class, that is class B. So you'll be having that luxury in class soft clustering, but whereas in hard clustering, you won't be having it. Okay, perfect. So next is your clustering. What are the different examples or what are the different use cases for clustering? Okay, one is your customer segmentation. So customer segmentation, what you'll be doing is this is common example for your e-commerce or retail shop, okay, where you will be having multiple customers. Depending upon the buying patterns or the demographic details like his age, his salary, his other normal details which is available, right? You can segment the customers into different ranks. So based on the ranks, you can just give them the advertisements which is required. Say for example, if a particular customer is more likely in buying cars or something, okay, you can send him more offers on that particular cars. Okay, so these are called as which you can do using your clustering algorithms. Okay, next is image processing. This image processing is mainly related to the biology stuffs. Okay, so where you will be having, you'll need to detect the patterns present in the images. And next is nothing but a fake news detection or a spam mail detection, where you'll be able to detect you'll need to find the differences between a spam mail or a fake news and a real news. So this is, you'll need to either cluster it into 0, that's nothing but a fake, and 1, it will be your normal news. Okay, great. So now classification is a common example of your supervised learning. Okay, clustering is the unsupervised learning. So let's both are, you will be clustering is grouping into different classes. Similarly, classification also, you will be putting the target data set test data into different classes. Okay, both the algorithms will be doing the same thing, but the only difference is classification is a supervised learning model. Okay, what it does is it learns from the trained data set, where you'll be having the outcome called as y variable. But whereas clustering is an unsupervised learning, so it tries to find a natural grouping present in the unlabeled data. Okay, that is called as your difference between clustering and classification. Okay, so this is your classification and this is an example for clustering. Okay, for the same weight and height, if you try to differentiate between children and adults, you will be having a sample data set for classification, but whereas in clustering, you won't be having any sample data set to do it. Okay, perfect. So now let's understand about, okay, what are good clustering algorithms? Okay, so what are good clustering algorithms are, it depends upon two main concepts. One is intra-cluster minimization and inter-cluster maximization. So what is intra-cluster minimization is, you can just see this figure. Okay, if you try to minimize the gap between the data points available within a cluster, okay, those are called as intra-cluster distance are minimized. Okay, but whereas if you try to maximize the gap between the interclusters, that is from this cluster to this cluster, if you try to maximize the gap, right, that is called as your intercluster. So if you try to maximize it, it's a good cluster. And similarly, if you try to minimize the gap between the data points available within the cluster, that is also a good cluster. Okay, perfect. So now let's try to move on to k-means algorithm. Okay. Okay, so what is k-means algorithm? So before I move on to spectral, right, I want to give you a background about k-means algorithm. So k-means is one of the basic type of algorithm which is used for your clustering technique. Okay, so I'll give you a background about how k-means works, then we'll move on to spectring. Okay, so it's spectral algorithm. Perfect. So first is k-means, right? K-means is a distance-based algorithm. So in all your distance-based algorithm, you should be having your data set that is nothing but of the features which are available for your available in the data set, right? That should be normalized. Normalized is nothing but the value. Say for example, if you have a feature called as age and the other feature is an income or salary, so what will happen is your age could range from 0 to 100, but whereas your salary could range from, say for example, from 10,000 to 1 lakh, if that is your salary range, right? What is the problem is your income will have more weightage than your age, because the range in which your income is there, right? It's more compared to your age variable. So what you need to do is you need to normalize the data set. The scale should be same between your age and your income variable. So this is what you should be keeping in mind when you do your k-means algorithm. Not only k-means, all your distance-based algorithm should be done like this. Okay, perfect. So okay, let's move on to k-means algorithm. So in k-means algorithm, k means nothing but the k denotes the number of clusters or in the particular data set. Okay, say for example, if we have, let's consider this to be a cluster. Okay, so I'll just take highlighter around. Okay, so this is a data points which is available. So in this data points, say for example 1 2 3 4 5 6 7 8. Okay, and there are 8 different data points present in this data set. Okay, so what I'm going to do is I'm going to associate all this thing to a single cluster. Okay, so all the data points is present is going to be associated to a single cluster, and that cluster will have a centroid. Okay, so this centroid is denoted with a black dot. Okay, say for example this whole 8.8 points has a centroid in this particular point. Okay, so next what you'll be doing is you need to have a you need to increase the number of clusters. Okay, say for example from 8 I need to increase it to 2. Sorry, so from one cluster I need to increase it to 2. So now I have two different clusters, so 1 and 2. For these two data points, or for these two clusters, I should be having a two different centroids. Okay, one for example for this data point the centroid is here, for this cluster the centroid is here. Okay, if I keep on increasing, right, you'll be finally reaching a place called as where you will be seeing 8 different clusters. Each data point is associated to each cluster, and that particular data point will be the centroid for that particular cluster. Okay, so if you are able to reach that point, right, you will be seeing an error rate of 0. That is what you'll be seeing in this particular graph. Okay, so this distortion is nothing but the error rate. When you have a one cluster, okay, your error will be more, because the error is nothing but the distance from this particular data point to the centroid. Okay, that is called as error. So when you have a error rate more, right, so obviously when you have one cluster you'll be having error rate more. When you have two, obviously error rate will decrease, but it will be comparatively more than 3. Okay, so this is how you need to plot these graphs. So this is called as your elbow method of determining the value of k. So how you'll be determining it is you'll be seeing a angle of 180 degrees. Say for example from this 1 to 2 and from this 2 to 3, right, you'll be it's close to some 180 degree here. But whereas from 3 to 4, where you have a k value as 3, there's a decrease in the angle. It could be some 120 degree or something. Okay, where you will be seeing a decrease in the angle. It's like normal human elbow. Okay, so you need to find this point and you need to fix this point as your k value. And you start increasing also, you'll be again seeing an value as 180 degree. Okay, so you need to fix this point as your k, and you need to go ahead and keep on repeating this particular method. Okay, so this is how you should be finding your value k. Okay, now once you find the value k, what you should be doing is, this is your first step in k-means algorithm. Once you have found the value k, okay, what you'll be doing is, so now our value k is 3. Okay, so in 3 we'll be having 3 clusters with each centroids, correct? So what you'll be doing each, so for example 1 2 3 4, so these 4 data points is associated with this particular cluster, okay, and these two data points is associated with this cluster, and two is associated with this particular cluster. So what it does is, this is a cluster with a centroid here, and this is a cluster with centroid here, and these 4 points is a cluster with centroid here. So this is our first iteration. Okay, so what you'll be doing, you'll be doing the process again. So now you will be slowly trying to move the centroid towards the data set, okay, towards the data point. So if you see, right, it has moved towards the left. So 1, 2, 3 is for this in this particular cluster with the centroid has been moved towards the left hand side. Similarly, 1, 2 is the cluster, and here it has been the cluster. The centroid is slowly moving towards the data set. 1, 2, 3 has been associated with another cluster, the third cluster with a centroid here. Similarly, in this next iteration, what you'll be doing is you will be reaching the place where you will be, it's called as convergence. So convergence is nothing but it's it's the state where you even increase the iteration, you won't be seeing any difference in the or shift in the data points. So that is called as convergence. Okay, so you need to repeat this until you reach convergence. Okay, so for example, here we have reached till second iteration, but in your case, if your data set is more, you can do it until you reach your convergence. Or if you want, you can even place the maximum iteration value. Okay, if your data set is hugely varying, say for example, if you have outliers in your data set, okay, outliers are nothing but your noise in your data set. Okay, if you have outliers, right, your data could be uh, that particular data point could be present somewhere outside that normal data range. So what you'll do is you need to do the iterations more. So in that case, what you can do is you can pass on maximum iteration value, which and I'll be showing you in the Python code. Okay, so you can pass a maximum iteration value, which will help you to not trouble the algorithm, so which will help you to easily compute the k-mean steps. Okay, so this is the clusters which will be changing depending upon the iteration. Say for example, now it's the 10th iteration. So if you see, right, slowly the clustering is changing. So this is what your iterations will do. If you keep on changing your iterations, right, your centroid and your clusters will change, and it will try to come to the convergence state. Okay. Okay, so before I move on to this, I'll just show you the code.
I think he got disconnected. Yes, he's back.
Okay, hello.
Yes, we can
Yeah,
hear you.
sorry, students. Okay, there's a power cut here. Okay, sorry. Dr. Bilga, can you just I'll share the screen, but I won't be able to share the video. Okay, is it fine? Because I'm just using my mobile data.
Yeah, it's fine.
Okay,
It's fine. No
sure.
problem.
Yeah, thank you. Thank you. Okay, perfect. Great. So this is the code for your k-means algorithm. Okay, let's try to I'll try to keep it simple so that we'll move to spectral clustering later. Okay, so this is a small data set. Okay, so I'm just importing the libraries which are required for your k-means algorithm. So numpy is for handling the numerical data like arrays, those stuff. Matplotlib is for the visualization, and scikit-learn is nothing but I'm importing the k-means stuff. Okay, so I'll just run this package, and I'm creating a array, numpy array. Okay, it's a two-dimensional array where I'm having values for my weight and height. Okay, so now I'm going to find a value k. Okay, so how I'm going to do is I'm going to pass it in a for loop. Okay, It's going to start from 1 till 5. Okay, so what I'm going to do is I'm going to run a for loop, and here I'm going to try to find the clusters which gives me the maximum the distortion. Okay, so distortion is nothing but the error. Okay, so if you see, right, and then once I got this, I will try to plot it using the matplotlib. So if you see here, right, this is the elbow chart which I'm getting. Okay, the k value I can easily find it to be 2. Okay, as we discussed earlier, the k value is 2. So now I'm going to do a scatter plot to display the data set which you have created. Okay, so this is the data set which you have created. So I'm just going to do a scatter plot of it. Okay, now I'm going to apply the k-means algorithm. So k-means algorithm, the first parameter is the k value, that's the n clusters, that is 2, and this is the maximum iteration value which I was talking earlier. So if you want to attain convergence, right, you no need to use you can remove that maximum iteration value. If okay, okay, so I have done the k-means stuff, and next I'm fitting that k-means to the data set which we got. Okay, the weight height. Okay, this is called as unsupervised learning. Okay, where you are not training any data set, you are running the algorithm, and next you're using your data which you are going to predict it, that you're going to run it. Okay, next I'm going to find the centroids for the clusters. Okay, so this is the centroids for the clusters. I am going to get 2 different clusters. Okay, I'll just show it in the graph also for you. So this is one cluster and this is one cluster. Okay, if you want, I'll just show it with the centroids also plotted. So for this particular cluster, this is the centroid, and for this particular cluster, this is the centroid. Okay, so this is called as k-means algorithm. Okay, now let's move on to. So I hope you guys would have got an idea about k-means algorithm, right? So now let's move on to spectral stuff. So before we move on to spectral light, there are 2 main approaches in clustering. Okay, one is compactness, that is nothing but your k-means algorithm. So how your k-means works is I'll just show it in the graph which is there. So your k-means is nothing but it tries to calculate the distance between the points, data points, and it tries to cluster the values in a circle, that's nothing but a sphere. Okay, so if it tries to calculate the distance between the data points, and it tries to group it into a cluster based on the centroid which is present. This is what we discussed earlier. But whereas what is connectivity is, connectivity is nothing but the data point should be either connected to each other or it should be present immediately next to each other. Okay, if that is the case, then you should be using connectivity approach. Okay, if it's not connected or if it's not immediately present next to each other, then you should be using compactness, then you should be using k-means algorithm. Okay, let's take this example. Okay, so this is something a complex figure than which we have discussed. Okay, so your data is connected with each other, so it starts from here, it goes in some spherical shape. Okay, so if you apply k-means on this particular data set, what will happen is it will divide your data set into 2. Okay, it ideally has 2 different starts. So this is your first data set, okay, first cluster, and your second cluster starts from here. Okay, it goes like this and it goes. Okay, but whereas if you apply k-means, right, as it is distance based, it will try to split the data into 2 like this. That is, whereas when you apply spectral clustering, right, you will be able to easily get your clusters which you are expecting. That is because it uses the connectivity approach. Okay, perfect. So this is the difference between k-means and spectral clustering. Okay, the same thing. Okay, so why we should be using spectral clustering? Okay, so this example we'll be taking and I'll be showing it to you. So for now, I'll let you know what I'm doing here. Okay, so these are just the packages which I'm going to import. Okay, so this numpy matplotlib and the k-means I already discussed, but This make blob is for creating synthetic data. Okay, so when you want to create artificial data instead of using a real time data, right, you can use here make blobs or make circles, those stuffs from your scikit-learn package. Okay, I'm going to take a sample size of 1500 and a random set as some random number. Okay, 170. I'm going to create use make blobs to create the random set. Now what I'm going to do is I'm going to create an anisotropic distributed data. So what is anisotropic distributed? That is nothing but isotropic if you have the data set in equal range. Okay, if the range is uniform, this is called as isotropic. The opposite of it is called as anisotropic. Okay, if it is in equal range, then you can go ahead and use your k-means. If it is not in equal range, then you can go ahead and use your k-means. Perfect. So now I'm just going to create a 2x2 matrix with numbers, and I'm going to do a multiplication with the data set which I have created. Okay, so this is done, and I'm going to try to plot it, use a scatter plot to plot the data set. Okay, this is the unlabeled data set. Okay, so here if you see, there's a connectivity part here, and the data points are connected in this particular cluster, and the data points are connected in this particular cluster. Okay, so there are 3 different clusters which are interconnected with the data points present inside it. Okay, but whereas if you apply k-means on top of this algorithm, okay, on top of this data set, what will happen is the same thing. It will try to split the cluster into, based on the distance, it will try to group the cluster into 2. So the first cluster will be like here, this, the second one will be like this, and the third one will be like this. So which is not you're expecting. Okay, so that is how your k-means will work. So that is mainly because the first cluster would have got a centroid in this particular place. Similarly, the second cluster would have got a centroid in this particular place, and third cluster would have got a centroid in this particular place. So this is how your k-means will work. Okay, so when you have your data linearly separable, then you can go ahead and use your k-means. But when you have a non-linear separable data like this, then you can't use your k-means. Okay, you need to use a spectral algorithm to do it. Okay, great. So now let's move on to spectral clustering. So what is spectral clustering? Spectral clustering is nothing but if your data is not in a it's not in an organized manner. Okay, it has multiple groups of data. Then what you need to do is you need to use spectral clustering to analyze the data, to analyze the patterns present in the data, and you need to put it in different groups based upon the uniqueness present in the data. So for that, you will be using spectral clustering. As we have discussed earlier, it will be using the connectivity approach for clustering the data set. Okay, spectral clustering will be treating the data as a graph partitioning problem. Okay, so what it will be doing is in this example. Okay, so for example, if your data set is, your first cluster is like this, your second cluster is like this. Okay, this is nothing but a moon shape stuff. Okay, so if you want to have your data like this, your data points are connected here, but whereas the same thing, if you apply k-means here, it will be, the data will be associated here. Okay, I'll be giving you an example using Python code also for this data set. We'll be discussing on it. Okay, similarly, if you apply clustering, spectral clustering, what will happen is your data will be properly grouped based on the connectivity approach. Okay, so what are the different examples for spectral clustering? So in common world now, we have the social networks like Facebook, Twitter, where we'll be having the data in somewhere like a graph format. Okay, so if you want to analyze that particular graph, then you should be using spectral clustering. Okay, and the next one will be your, for example, tracking of your inline and outline of web pages. If you have any e-commerce website or any web page. Okay, if you want to track the number of users who are viewing your web page, some of the users who are paying the payment stuff in your web pages, right? If you want to analyze those things, then you should be using your spectral clustering algorithms to do it. Okay, because the data set is present in the form of a graph. So what we can do is we will be discussing about the different concepts present in spectral clustering algorithm. Okay, so spectral clustering algorithm can be broken down into 3 basic steps. So first one will be, we need to create an affinity matrix. Okay, so for now we'll be concentrating on this particular first step, what is affinity matrix. Then we'll move on to diagonal matrix and Laplacian matrix. Okay, so for now we'll concentrate on what is affinity matrix. Okay, so we'll take this particular stuff. The affinity matrix is nothing but similarity matrix, okay, where if you have a value close to 1, then you can say that the points are nearby, and whereas if you have a value close to 0, then you can say that the values are not close to each other. Okay, there are many ways to create an affinity matrix. Okay, we can use, for now we'll be using the Gaussian kernel technique. So this is the formula for the creating the affinity matrix, which we'll be deploying it in Python also. I'll be showing you with an example also. Okay, so in the form of graph, right, we will be having a concept called as adjacent matrix. Okay, what this does is, I'll just show it to you. Once I explain the whole thing, right, I'll just go to this particular web page. It's nothing but a Wikipedia web page. So you can just go over this particular stuff. If we don't have time, you can just go over it, or if you have time, I'll just go over this particular web page and I'll show it to you how this adjacency matrix looks. Okay. So for now, I'll just go to the Python code and I'll explain to you how this we are going to get the affinity matrix using this particular formula. Okay. So here I'm going to import the packages NumPy, makemoons for creating the data set, similarly macblobs, and kmeans is for using for from the scikit-learn, and I'm going to use it for applying the k-means algorithm. Spectral clustering, at the last I'll be showing to you how we can directly apply spectral clustering on it. Okay, and similarly matplotlib is for plotting, and metrics is for showing. And here metrics, the pairwise distances is nothing but, in this particular formula, xi minus xj. Okay, xi minus xj is nothing but the absolute value of the distance between a particular point I and j for the data point x. Okay, that is what this xi minus xj denotes. So we are going to calculate the distance using the pairwise distance present in the scikit-learn package. Okay, so I'm going to import the packages which are required. Now let me try to create the data set which we saw in the example. Okay, so this example here we have two clusters. One is cluster 1, cluster 2. Okay, and now we already know that if we apply k-means on top of this, okay, what will happen is we'll be getting an answer similar to like this. Okay, so this similar to this, we'll be getting an answer. So I'm not going to show you how why we are getting, okay, how we are getting it. Okay, we already discussed how to apply k-means, so I think that should not be a problem. Now I'll just go directly to the steps which is involved in the spectral clustering. Okay, so first step is we need to create the affinity matrix. Okay, in affinity matrix, we'll be using the formula exponential from NumPy package, and this is nothing but the formula which is present here. Okay, so this is the formula which you're going to use, and for calculating the distance, we are going to use the pairwise distance, okay, method. And Euclidean distance is what the metric we are going to calculate it for this x array. Okay, and here this value, this one, is nothing but this parameter. Okay, the Gaussian parameter. So for this one, I'm going to pass 1. I'll let you know how to do it. Okay, for now I'm just going to pass 1. Okay, let's see what happens. Okay, so we have created an array which is a 2-dimensional array which has values in it. Okay, now let's move on to the next step, the diagonal matrix. Okay, so your first step is half done. Okay, so this is your major step which you will be creating the affinity matrix. So this is half done. Now let's move on to diagonal matrix. Okay, so what is diagonal matrix is nothing but, if here in diagonal matrix you'll be using this particular formula, you will be just summing the values which is present in the affinity matrix, okay, for the endpoints. So you'll be just summing the values and you will be having the values only in the diagonal. So that is what is a diagonal matrix. So we have created a diagonal matrix. Now let's move on to the Laplacian matrix. Okay, so Laplacian matrix is generated using the formula. You can use any of the formulas. Okay, so starting from simple Laplacian, you can just do a subtraction between the diagonal matrix and the affinity matrix. But for now, I'm going to use this particular formula, okay, to calculate the Laplacian matrix. So I'm using the power method from NumPy package. The same thing. Okay, instead of half, I'm going to pass 0.5 and going to multiply a into the minus 0.5. Okay, so this is done. So I have created the application matrix. Now let's move on to the next step. So next step is nothing but we need to compute the eigenvalues and eigenvectors. Okay, so what is the I'll explain why we need eigenvalues and why eigenvectors. How to compute eigenvalues and eigenvectors is a huge concept, guys. Okay, so I won't be able to complete it now. So I'll just for now we'll just take help from Python to compute it. I'll let you know what is the use of computing the eigenvalues and eigenvectors. Okay. Okay, we'll just concentrate on this particular graph. Okay, so if you see here, right, whenever we connect a point, the points from 0 it starts increasing. So this is what your eigenvalues will do. So this is nothing but when there is no connection, your all the values will be present in 0. Okay, when you start connecting the data points present in the graph, okay, then what will happen is you will be seeing a increase in the value. But this 0, the first point, okay, the first point 0, what it denotes is you could see a one connected component between these two subsets. Okay, if say for example, let's take this particular graph. If you want to divide it into two different subgraphs, okay, this could be one subgraph and this could be one subgraph. Okay, and between these two subgraphs, I'll be able to see only one connecting point. That is nothing but it moves from 5 to 0, or it could be from 0 to 5. If it is directed graph, it could be from 5 to 0. If it is undirected, it could move from multiple directions. Okay, so that is what this eigenvalues will give you. Okay, so what we should do is we should not take this particular eigenvalue 0 1. You should be omitting this particular thing, and we should be taking the second eigenvalue, that is your called your filter value. Filter value is nothing but the second highest value. That's apart from your 0 value. If you have one connected value, it will be one, you'll be seeing only one zero. So if you have two connected values, you'll be seeing multiple zeros. Okay, in our case we could see more number of zeros because our case is huge. It's almost most of the data points are connected, right? So we will be seeing many number of zeros. Okay, we will be taking this particular eigenvalue and this particular eigenvector to compute the, for that particular data point we will be computing the k-means algorithm. Okay, so that is will be your step 3. So if you so this will be your step 3. Before we apply k-means algorithm, we will be normalizing the eigenvectors and be applying the k-means algorithm. Okay, I'll show it in the Python code. So your first step is done. Let's move on to the second step. So we'll be using linear algebra from NumPy package to compute the eigenvalue and eigenvectors. Okay, so for now I'm just storing vectors as v, but eigenvalue I'm just, as we are not going to use it, I'm just going to keep it as a dummy value. Okay, so in our case we have only two clusters. Okay, we want to, in this example, okay, we need to split it into two clusters. So what I'm going to do is I'm going to select only the two column values from this particular vector. Okay, so I'll just try to print it. Let's see what we get. Okay, you could see a j at the last. So what it denotes is these are complex values. Okay, so I'm going to convert it into a, and remove this particular j, and I'm going to convert it into the real values. Okay, so which I'm going to apply the real method. So now the same thing, I'm going to extract the two columns around. So now we got the value. Now let's try to normalize the eigenvectors which we got, and let's try to use k-means clustering on top of it. Okay, so let me try to, okay, this plot, okay, what it denotes is, I'll let you know. Okay, so for now you can just consider this to be a scatter plot. Okay, and it has the data from your eigenvectors. Almost all the data set is connected. Okay, that is what this denotes. Okay, for now we can just consider that. Let's move on to the next thing, and I'll let you know what output we're getting for the k-means thing. Okay, for I have just applied the k-means stuff, and I'm predicting it for the eigenvector, the selected the first two columns of the eigenvector alone. Okay, so this is done. So what you're getting, it's similar to that of your k-means output, correct? That is what you're getting. So your clusters is not, this is not first cluster, this is not your second cluster. What it does is, this is your first cluster and it tells this is your second cluster. That is mainly because in the starting first phase, okay, if you remember, we would have created a passed a value 1, correct, for that gamma. So gamma is nothing but the Gaussian expression. So for starting phase we did it. So this is where we, for this particular value gamma, we passed a value, sorry, sigma, we passed a value 1. Okay, instead of 1, why 1 is causing a problem is, if you see here, right, in this particular graph, the distance between the 2 points is less than 0.7. Okay, the 2 data points are less than 0.7. So when you give 1, what it denotes is that when you pass 1, right, what it considers is, okay, 1 will be the nearby point. Till 1, I can consider that to be a nearby point. So I can consider that to be cluster in present in a single cluster. Okay, that is what it denotes. So what your algorithm will do is, till if it's present till one value, right, one distance value, what it denotes is, okay, that will be present in one particular cluster, and this will be present in one particular cluster. So this, it considered this to be one cluster and this to be another cluster. So that is what your algorithm has taken. So what you can do is, now you can just, instead of passing 1 in that sigma value, what you can do is you can pass any value less than 0.7. Say for example, I'll take 0.2 and I'm going to square it and I'm going to pass it. Okay, so if you see here, the formula is I'm going to square it. So 0.2 into 0.2, it's 0.04. I'm going to pass this particular value. Let's see what happens. So I'm calculating the affinity matrix. I'm calculating the diagonal one. Next will be my Laplacian. I'm calculating the eigenvalues and vectors. I'm going to select, for 2 clusters, I'm taking the first 2 columns. I'm going to normalize the values. Let's try to do scatter plot here. If you see, right, you could see a separation here. Earlier you would have not seen that. Okay, now let's try to apply k-means on top of this particular data set and let's see what happens. Okay, now if you see here, right, your groups or your clusters is almost correct. So you could see some discrepancy here. That it's not a problem. Okay, in every algorithm you'll be seeing some discrepancies. Okay, 2 or 3 data points are causing a problem. That should not be a problem. Okay, great. So this is your how you'll be doing your spectral clustering algorithm. Okay, so for this is how you'll be doing it using your formula stuffs. Okay, so apart from here, what you can do is you'll be also having a direct method, okay, for applying your spectral cluster. So I'll be going over that particular thing with an example. So this is a different example, which I think, so this example is this one, guys. Okay, so this is nothing but, yeah, this is the data set, right? So this data set I have chosen as an example. I'm going to implement spectral clustering directly to this particular data set. Okay, so first I'll apply k-means and I'll show you how the data looks. So it's similar to this. Okay, your data is present. This is your first cluster, second cluster, and third cluster. So similarly, first, second, and third. So now let's try to pass the spectral clustering. So if you do that, right, your clusters are clearly fine. So this is your first cluster, second cluster, and third cluster. So this is how your spectral clustering will be able to easily find out the different clusters present in a graph, or if it's present in a complex structure, right? Like if it is connected in, if it is connected, if it has multiple connectivity there, then what you can do is you can use your spectral clustering to plot it. Okay, to find the clusters available in the that stuff. So now let's move on. I'll just show you what this affinity is. Okay, so here we need to pass a value nearest neighbor. So I'll let you know what this affinity is. Okay, so this is the adjacency matrix which I was talking about. Okay, so adjacency matrix, I'll take this label graph as an example so that it will be easy for you. Okay, let's consider this to be a simple graph. Okay, so this is a simple graph. It's an undirected graph. What is undirected graph is, it's a directed graph. For example, it's a direct graph from 3 to 4. the data will move from 3 to 4 alone. It won't move from 4 to 3. If it's an undirected graph, you'll be seeing data movement from 3 to 4 and 4 to 3 also. Okay, that's what is an undirected graph. Okay, perfect. So this is the adjacency matrix which you'll be getting. Okay, how this one is calculated is you'll need to plot the values from 1, 2, 3, 4, 5, and 6. Okay, so you're just keeping your values here in column wise and row wise. Okay, so 1, 2, 3, 4, 5, 6. Similarly, 1, 2, 3, 4, 5, 6. Okay, so now for 1, okay, you will be first. Let's skip this one. Okay, let's move on to this particular thing. 1 and 2, it is connected, so you'll be passing 1 here. Okay, whether 1 and 3 it's connected, no, it's not connected, so you'll be passing 0. Similarly, 1 and 4, whether it's connected, no. So 1 and 5 is connected, so you'll be passing 1 here. Similarly, 1 and 6 are not connected, so you'll be passing 0 here. Okay. So now let's move on to 2 and 1. 2 and 1 is connected, so it's 1. So similarly, you'll need to plot it for each and every data point, starting from, for if you have 6 data points, right, you'll be seeing 6 different values in your columns and your rows. So this is called as your adjacency matrix. Okay. So this is how you will be plotting your adjacency matrix. So if it, when you have your complex structures, okay, if you have a graph like this, then you'll be seeing a complex adjacency matrix. Okay, so this one will be, I think for this, you can directly use your affinity matrix itself. So instead of, you can directly apply the formula which is present here. Okay, instead of directly using adjacency matrix, what you can do is you can directly apply the formula which is present here. Okay, great. So okay, I think I have, okay, so for now, just I have given you a background of about how your spectral clustering works and how it is done. Okay, it's spectral clustering itself is a very huge topic. Okay, so I think within 1 hour data frame, I have just covered a simple, okay, I just took this particular example, the Laplacian, the last one I covered it. There's uh, instead of covering a simple Laplacian, okay, simple Laplacian will be a little more easier than this one, but the problem is you won't, if you have to handle a complex data set like the data sets which we saw, okay, like this or some, okay, like this. If you have a complex data set, right, what you need to do is you need to use the Jordan and Weiss Laplacian method. So this 2 and 3 is nothing but, it's nothing but a normalized form. Okay, so once you have your L, if you want to normalize it, you need to multiply, use this formula to do it. And generalized form is nothing but your, once you have the diagonal matrix, you need to apply -1 to the power of, and you need to multiply it to this one. So 2 and 3, it's not that much important, but whereas you can just understand what is this simple Laplacian and this stuff. So this 2 should be more than enough for you guys. Okay, great. So I think this is fine. Okay, any doubts, guys, this session? If you guys have any doubts, no, it's open to questions. So I think still we have 5 more minutes. You can ask your doubts or questions.
So, compared to supervised learning algorithms, why is it beneficial for, let's say, someone to use a unsupervised machine learning algorithm?
Okay.
If they do.
Okay, sure. So supervised learning algorithm, right? So when you have a data set, okay, a training data set available, okay, can directly go ahead and use a supervised thing, okay. But in real life, you won't be having that luxury always in your hand. So what is the problem is, say for example, if you have given a direct live data of from a bank system or something, okay, if they ask you to predict the fraudulent transaction which is happening, and you don't have the history data which is available for applying the supervised algorithm. So what then you can do is you need to apply the fraudulent detection method to do it from unsupervised thing. So in real world, always you won't be having that particular luxury. For learning purpose, starting from supervised learning should be fine. But obviously, when you go to the market stuff, right, you won't be seeing that particular thing.
Yes, sir, got it.
Okay. Any other doubts, guys?
So, if you don't have further questions, shall we wind up, sir?
Yes, Dr. Bilda, we can do it. Yeah.
Okay, thank you. So let's wind up then. I thank Department of Computer Science Engineering, AI, ML, and Cybersecurity and Futurance Technologies for the efforts they take to organize these industry connect sessions for our students. We are grateful to our resource person, Mr. Daawood Sheikh, for conducting this session for our students. Thanks are due to Dr. V. Vivek, the head of the Department of Computer Science Engineering in Artificial Intelligence and Machine Learning and Cybersecurity, for flawlessly coordinating the activities of the department. I also thank our team of faculty members for always supporting our students in academic and non-academic activities. Students, we appreciate that you make use of these sessions. Please don't forget to fill in the survey form before you leave. So I think let's call it a day then. Meet you next week. Good night, everyone.
Thanks, Dr. Bilga. Thank you.
Thank
Thanks
you.
all.
Thank you,
Thank you,
sir.
sir.
Thank you.
Thank you. Bye-bye.